All right, so the first one, we had a few different techniques we can use. First off, noticing that there are two congruent marks, we know that these two angles have to be 45 degrees each. Knowing one of those angles then is enough, along with one additional side length, we can just use basic trigonometry like SOHCAHTOA, sine, cosine, or tangent, to determine x. So if you recognize that this was a 45-degree angle, you had, I guess, three different options altogether. You could first say that, set up a little trig equation. If you take, let's say, this angle down in the lower right, with that 5, you could say something like, well, the cosine of that 45-degree angle, cosine is adjacent over hypotenuse. The adjacent leg would be this 5 that's given to us, and the hypotenuse is x. And then we can solve that for x. Another technique that we could use is, if these two angles are the same, then I know that these two legs have to be the same, 5 and 5, and we could use the Pythagorean theorem, right? If you know two sides of a right triangle, you can use a squared plus b squared equals c squared to find that third length. So we could say 5 squared plus 5 squared equals x squared, and solve that for x, and we'll get the same answer. And there's a third thing. You also might have recognized that 45, 45, 90, that's one of our special right triangles, and we have a shortcut. This would probably be the easiest and quickest way to get an answer for this one, is knowing that the legs are the same. The hypotenuse is simply that same short leg length of a 5 times what value? Square root of 2. So you could also just say, hey, x equals 5 times the square root of 2. And all three of these techniques will give you the exact same value. Well, a decimal, right? You're going to round them off if you multiplied out like 5 times root 2. And what did everyone get for this one approximately? What? 7.07. Anybody else? 7.07? Thank you. So it was approximately 7.07. Awesome. Right, and all those techniques will give you that. Or instead of cosine, I could use sine, right? If I use this angle up here, I could say the sine of 45 equals the opposite over hypotenuse. All right, so I guess there's 4 different techniques, and all of them will give us the exact same answer. It's crazy. Lots of ways to solve for that. Now, this middle one right here, solving for y, has fewer options because it's that 70-degree angle. In this case, it's not a special right triangle. I don't have any information about the other, like that bottom leg. And so I would just use basic trigonometry, SOHCAHTOA. And I look at the angle that's given to me, that 70 degrees right there, and I look at the two sides, the one that's given, the one that I'm looking for, the 8 and the y, and I see that 8 is on the opposite side and y is the hypotenuse. And so I would set up a little trig function with sine, because in SOHCAHTOA, that's SOH, S-O-H, is the opposite over hypotenuse. So we can say the sine of 70 degrees equals 8 over y. And then we would just solve that for y, right? You'd bring the y to the left, move sine of 70 in the bottom, and you'd essentially calculate 8 divided by the sine of 70. And what do we all get for that? What did you get? 8.51. Did anybody else get 8.51 approximately? Excellent. So that's approximately 8.51. Very cool. All right, and then the last one, solving for w. We have two angles given, one side length, and you need that other side length. Let's see. Can I use the Pythagorean theorem on this one? No, we can't. I only have one side length given. I need at least 2 of them. What about SOHCAHTOA, trigonometry, right? Can I use like sine, cosine, or tangent? Would that work? Actually, no. Special right triangle. You see, SOHCAHTOA, like your basic trigonometry, and the Pythagorean theorem, and those special right triangles, unfortunately, they all deal with right triangles. Now, right triangles are very common in the real world. If you think of any structure, a building, a tree, something that grows straight out of the ground, it's perpendicular. It makes like a right angle with the ground. And so looking at anything from the side, we often see lots of right angles. Look at the windows, look at the floor, the ceiling, right? There's right angles everywhere. And so right triangles are very common in our world. However, there are also lots of triangles that are not right triangles in our world. All right. So right here is an example of a triangle. Maybe this is the layout of I don't know, someone's garden in their backyard, and they're trying to figure out how much fencing they need on each side or something like that. And it's not going to be a perfect right triangle shape. Maybe there's rocks over here or there or something like that. And we need to figure that out. Well, unfortunately, with the tools that we have right now, we can't use them. You can't use sine, cosine, and tangent in the normal way. We can't use a squared plus b squared equals c squared. Those are only used for right triangles. And there's one angle that's 90 degrees. And that's not 90, that's not 90. And if I subtract those both from 180, well, then we see that this side is 40. So that's also not a 90-degree angle. So this isn't a right triangle. So we can't use any of those. Luckily, we do have a way that we can still solve for those unknown lengths or angles in non-right triangles. That brings us to today's lesson. Dun, 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 dun. You're excited now, right? Because you want to figure that out. How do you solve for that? I can't wait to find out. Well, we use something called the law of sines. This is the first actual learning target that you will be assessed on in this unit. Target 9.1. And there are two different laws we're going to learn this week. Today, we're going to focus on the law of sines, which is basically just a formula that allows us to solve for side lengths or angles of non-right triangles. All right, so that's the key thing here that you should highlight or emphasize. This is for non-right triangles. So any triangles that don't have a 90-degree angle, we can use this law of sines. Which again is pretty useful because not everything in the world is at a right angle. A lot of things are, but not everything. Then on Friday, we're going to learn something called the law of cosines. And so this is going to be your first learning target. So the law of sines. This can be used to solve right triangles, but only if you're given certain pieces of the triangle, right? So if I have a triangle and I only have one side length and no other information, this isn't going to work, right? I still need some additional pieces of information, just like with trigonometry, Pythagorean theorem. I can't always solve everything if I have only one piece of information. I need some additional info, either on the angles or on the side lengths. And so here's the key things that you need for the law of sines. Now, here's the easier way to think of it. Basically, look at the triangle diagram. So, I don't know, those bullet points, that's like the textbook definition. I prefer what's written in blue. Look for an angle across from a side length. Right? That's the key thing that you need to use the law of sines. You need to know one angle on the triangle, and you need to know the side length that's across from that angle. That's the key thing that you need. So don't worry about those bullet points. Those are just fancy terms that get confusing. But basically, you need a triangle where you have, like if I've got this angle here, and I'll call that like angle A. If that is actually given to you, you know it's like 20 degrees or whatever, you would also just need the side length that's across from it. Okay, that's what you want to look for. If you see in your triangle, I know the angle and I know the side length that's on the opposite side from that angle, then we can use the law of sines. But if you don't have that combo anywhere on your triangle, then we can't use the law of sines. We got to use something else. But that's the key thing that you're looking for. And as long as you've got one one combo of one angle with the side length across from it, and it can be any angle with the side across from that respective angle. If you have that information, then you can solve for any other side length and any other angle, which is pretty cool. So yeah, you need that combination, and then any one other angle or side length is fine. So one of the other sides or one of the other two angles, doesn't matter which, but that's the key thing that we need for law of sines, the angle and the side that's across from it. Now the law of sines is just a simple formula. It's very basic. It's barely even a formula. It's just like a relationship, a ratio. Here's what it looks like. So here's the law of sines on the left. And there are three different ratios. There are different fractions that are all equivalent. Now, you don't need to have all three of these fractions or anything. It's just saying that all three of these combinations. So I want you to very carefully draw any triangle diagram, but the labeling is where it's going to be very important. So if you look at this triangle on the right, the way that I've labeled it is essential. This is what you need to start doing from now on. Whenever you're given a triangle, and we're going to want to label the sides and the angles. What we do is we always label angles with capital letters, and we label side lengths with lowercase letters. But look closely at how I'm using the same letter that's across from the angle of that same letter. So look how side A is across from angle A, because those are like a matching pair in essence. They go together, and you need that combination in order for the law of sines to work. Like that first ratio says the sine of angle A divided by the side length of A. And side length A is going to be always across or on the opposite side from that angle. Same thing, angle B is across from side B. So here's what I mean. Like here's angle A, and then on the opposite side of the triangle is side A, lowercase for side length, capital letters for angles. We need to use this same naming scheme. Angle C, capital C, and across the triangle from angle C is side length C with a lowercase c. And same thing with angle B, capital B for an angle, and across from it is side length B. That's just how we're going to be labeling them. This is true both for this law of sines, and we're going to use the same pattern for the law of cosines on Friday. Now, the way that this law works is we actually only need any two of these fractions to be equal. I don't need all three of them. This is simply setting two fractions or two ratios or proportions equal to each other, and then we cross multiply. Do you remember doing that in old school math? Here's just a simple problem. If I have 2 over 8 equals x over 4, remember when you'd have a fraction like this with an unknown, to solve for it, you use cross multiplication. You basically say, oh, well, this first diagonal, multiply that together, it's going to equal this diagonal multiplied together. And then you solve that equation for x. We're going to use that exact same process here with this law of sines. I'm going to pick any two of these, and they're all equal to each other. So it doesn't matter. I can do a with the b, I could do the b fraction with the c fraction, or I could even do the a fraction with the c fraction. It doesn't matter. All three of these ratios are equivalent. If you take the sine of any angle and you divide it by the side length that's across from that angle, and you divide that out, you'll get the exact same decimal if you take any other angle in that same triangle and divide it by the side length across from it. And same thing with the third angle. You take that third angle, take the sine of it, and divide it by the side length that's across from it, you're going to get the same decimal for all three of those. So all three of these fractions would equal the same exact decimal. The ratios are equivalent, and that's true for every triangle, whether it's a right triangle or not. So what we're going to do, and this is why we need to have, as I stated before, that pairing, that special combination of like one angle across from the side length, because I need one of these fractions to be complete. I need the numbers on the top and on the bottom of at least one of those fractions, right? I need A and A, or B and B, or C and C. Then I set it equal to any of the other ones where I have either an angle or a side length, and we cross multiply to solve for that one unknown. Pretty basic calculations. So, I mean, the only thing you really need to work on here is realizing the naming combination, right? Like take an angle, match it up with the side that's across from it. Also, I also do want to point out that since these are ratios, I could flip all these upside down and it'd be the same thing. So instead of doing like the sign up top, I could say like A over sine A equals B over sine B. It doesn't make a difference. If you flip both fractions, you're still going to get the same thing. Because like the reciprocal of something equals the reciprocal of the same thing. So you might see some problems where it gives you it this way instead. It doesn't make a difference if you're flipping both sides of a fraction on an equation. It's going to be equivalent still. Because ultimately when we cross multiply, it doesn't matter what was on top and what was on the bottom. We'd get the same thing. So let's go ahead and try this. Go ahead and draw this triangle out. And label it with those three values that are given. You have one side that's a 10. That's very important that we're labeling the angle that's across from the 10 is the 25 degrees. That's the important part, that you've got these in the correct spots. And then you have that other angle of 30 degrees. And we'll do this together. So in order to use the law of sines, I mean, first look at the triangle. Is it a right triangle? No, it's not. So then we're going to have to use the law of sines. And in order to use the law of sines, we need a side length and the angle across from it given. Do we have that combination here? Do I have one angle and the side length across from that angle? We do, right? I've got this combo right here. The 10 is a side length across from the 25 degrees, okay? Now to help me think about how to set up this law of sines, I'm going to label each angle and each side length with my A, B, and C. It doesn't matter which is A, which is B, and which is C. But what we do need to do is make sure that if I label, this angle A, I need to make sure that if I go across that angle, I'm going to do a lowercase a for that side. Okay, that has to be that combo. They've got to go together, those opposite sides and angles. So then over here, if I say that this 30-degree angle is B, then across from that is going to be a lowercase b. And finally, the angle down at the bottom, I'll label that 25-degree angle capital C, meaning that 10 has to be my lowercase c. Now, it doesn't matter which angle I label A, B, and C. I could have labeled the 25-degree angle capital A. But if I did that, that would just mean that my 10 side length would be a lowercase a. So you've got to make sure that you've got these combinations across from one another. So now we want to set up our law of sines. We always start by writing the one fraction with the two givens, the angle and the side length that are across from each other. So that's going to be the 10 and the 25 degrees. And so I'm going to start by writing the sine of 25 degrees divided by 10, because that's one of my pairs, one of my combinations of an angle with the side length across from it, right? The 25 degrees is across from the 10. So that's one fraction. Now, For my second fraction, remember, we don't do all three at once. We just always have just one fraction equal to one other fraction. And I can do it with like the b's or the a's, it doesn't matter. But looking at this triangle, I only have one other value given. Is that other value for b or for a? It's the b, right? That 30-degree angle is b. So I know that this next fraction has to be for the b angle in the b side. Because that's the only other value I have. If I did it for a, well, I don't know what side length a is. I don't know what angle a is. So if I made a fraction with sine of a over side a, I'd have two unknowns, which I can't solve for. And so instead, I'm going to use the b, angle b, and side length b. Remember, you always use those combos in a single fraction with the law of sines. I'm using this because I know what angle b is, or if I knew what side length b is. Those would tell me that that's what I need to use right here. So I'm going to say the sine of 30 over, and this has to be over side length b because it's across from angle b. They always go together. And if I look at that equation right now, it's an equation because there's an equal sign. There's only one unknown. There's only one variable, and that is that lowercase b, which refers to the side length. Anytime you have one fraction equal to another fraction, the way that you solve it is by using cross multiplication, which is a very simple process. All you do is you take one diagonal and you multiply it together. So I'm going to say 10 times sine of 30, 10 times the sine of 30, and you set it equal to the opposite diagonal. And again, you're multiplying these diagonals. So it's equal to b times the sine of 25. B times the sine of 25 degrees. I could have done sine of 25 times b, but order doesn't matter when we multiply. It's commutative, as long as these aren't matrices. Okay, so I'm solving this equation. Remember, there's still an equal sign. I want to get the variable by itself. That variable is the lowercase b. How would I get that b all by itself on the right side? What do I need to get rid of? And how can I cancel out that sine of 25? Let's just divide both sides, right, by the sine of 25 so that it cancels out. So I'm going to divide by sine 25, but then it means I have to divide this side by sine of 25. When I do that, the sine of 25s on the right cancel out, and we're left with just b all by itself, side length b. Now, what is the value of b? Well, if I look at the left side of the equal sign, I have 10 times the sine of 30 divided by the sine of 25. Now, those are all just numbers. I can just type that right into my calculator, and I'm going to get my value of b. So go ahead, take your calculator, and tell me what b equals. 10 times, the sine of 30 divided by the sine of 25. So we can just type that directly in. What do we need to make sure about our calculators, though, before we start using trigonometry? Degree mode. Yeah, remember, check your mode. Make sure you're in degree mode. I'll pull up my fancy calculator too. All right, so I'm going to mode, make sure I'm in degree mode, which I am. Second quit. Then I just type in 10 times the sine of 30. Make sure you close off the parentheses because you're doing the sine of 30 degrees. Close the parentheses, so you're only taking the sine of the 30. Divided by the sine of 25. Anyone else get 11.8? Yeah? Fantastic. Great job. 11.8, approximately. 11.8. So that is side B. 11.8 is approximately equal to B. Cool. Now my directions up here, though, they actually said solve the triangle. And solve the triangle means you have to find all the angles and all the side lengths. But the issue here is the side and angle that I don't have is A, and I don't have either of those values. So I couldn't set up a ratio of sine of A over side length of A, because they're both two different unknown values. Capital A and lowercase a are different numbers. And I can't have two unknowns in a single equation. I can't solve it that way. Do any of you have an idea of how I can actually figure out what side length A is, or perhaps what angle A is? What do all three angles in a triangle add up to, Slim? 180 degrees. Do I know two of those angles already? Yes. Can we figure out that third angle pretty easily? Yeah. Can you figure it out right now for me? You can use your calculator if you'd like. He's getting it. He's going to get it. 125, survey says? Yeah, you got it. Nice job, man. So, how do we figure that out? We didn't know angle A. Boop. But since I knew that angles B and C were 30 and 25, and all three angles in a triangle had to add up to 180 degrees, I can just say, well, angle A equals 180 minus those other two angles that are given. Subtract the 30, subtract the 25, and we see that angle A equals 125 degrees. And so that gives us another value, 125 degrees. And now for the law of sines, I can complete that because I know angle A, I can solve for side A. Oh, actually, wait, if I know these two sides, can I just use the Pythagorean theorem to find the last side then? Right? A squared plus B squared is C squared? No? What do you mean no? Why not? Oh, it's not a right triangle, so we cannot use Pythagorean theorem. Now, on your test, there's going to be a section called Law of Sines. To solve for those, use the law of sines. Believe it or not, kids will still use Pythagorean theorem right there. Because you're like, oh, I've got two sides, use the third one. But no. Come on, it's algebra 2. We're not using some basic Pythagorean theorem. We're more advanced than that, right? We're like geniuses. So I'm going to set up this same ratio again. Now, initially I used the C, the 25 degrees and the 10. But now that I know B, angle B and side B, I could use that also as my first fraction where I've got my two values, my numerator and denominator. And we'll get the same answer because all three of those ratios will equal the exact same thing, the same proportion. So it's up to you if you want to use B, if you want to use C. Any preference? Anyone want to pick one or the other? What'd you say? B? All right, let's use B. That's the new one. So I'm going to start by writing the fraction where I know the angle and the side across from it. So I'm going to say the sine of 30 divided by the side length that's across from it, and that's what we just calculated the first time we used the law of sines on this problem, and that's 11.8. Equals. Well, now I need to make my second fraction with the one side that we're looking for, which is A. So I need to put sine of A up top and actually know what angle A is. So I can do sine of 125, divided by lowercase a. And that's the last side length that we're solving right now. We're looking for that side length A. At this point, I've got two fractions equal to each other. We just use cross multiplication. So everybody, you should all be able to do this pretty easily. Just crisscross applesauce. Should take one diagonal. Should say 11.8 times the sine of 125 equals the opposite diagonal, A times sine of 30. Then to solve for A, just divide both sides by the sine of 30. Eventually you're going to get pretty quick at doing this. I actually am at the point now where if I see one of these ratios, I look at the one unknown. And I know that the way that I solve it is I multiply the values that are diagonal, and then I divide by that last number that's left out. It's kind of like a quick little shortcut. You're going to get the same thing. We are using cross multiplication and solving, but essentially after I've got the ratio set up, I multiply the two values that are diagonal from each other. So 11.8 times the sine of 125, and then you divide by that one number that gets left out. That's not part of that diagonal. So divided by sine of 30. Anybody else get 19.3? Yes! Huge. So A is approximately 19.3, right, Slim?
Yeah.
Let's see.
20.4.
She did 120 instead of 125. This this digit right here is called a 5. It's close to a 0, but it's 5 away from it. It's actually the one digit that's as far away from a 0 as possible. Because you got 0, then you got 10. 5 is right in the middle. It was silly. No big deal. Happens to me. I make silly mistakes. All right. So that's how we use the law of sines. What do you think? Is this like the most difficult, craziest thing in the world you've ever done? No, it's not bad at all. Any questions on this before we practice a few more? All right, let's see you do one on your own. Solve the triangle. Oh, wait, actually, I'm going to help you with this one a little bit. It does have one new thing. Go ahead and draw it. Doesn't matter which angle or side length is initially the A, B, or C. What's the one thing that does matter, Carson? Yes, across from it, right? Just make sure you label across appropriately. So wherever you start with A, B, and C, it doesn't make a difference. But then make sure that angle or that side across from it does match with the same letter, just capital versus lowercase. Capital for an angle, lowercase for a side length. So I'm guessing maybe most of you did something like this, just alphabetically A, B, and C. If you didn't, that's fine. Don't worry. And then I'm going to go ahead and label the parts across from each of these. So this 18 will be my B, and the 13 will be my A, and C is this unknown. So first off, can I use the law of sines for this problem? Do I have that matching set that I need? We do, right? We have an angle across from a given side length. We've got the A combo. So I'm going to start by making my first fraction. with the two given values. So the sine of 40 divided by 13. Now, the only other given piece of information I have is side length B. So I'm going to need to figure that out next. Now, the side lengths go in the denominator. That's 18, or at least in my case it is. Again, you could flip these if you flip both sides. And in the numerator, I'm going to write the sine of angle B. So this one's a little bit different because you're solving for an angle. And you're going to have to use an inverse. Spoiler alert. So we're still going to cross multiply as usual. I always multiply the given diagonals first. So we're going to say 18 times the sine of 40 equals that opposite diagonal of 13 times the sine of B. Now I'm solving for B, which is an angle. And I can't just get rid of that. I can't divide out the sine. I can divide out the 13, which I'll do that first. And I'm going to rewrite this to put the angle on the left. So I'm going to have the sine of B equals 18 times the sine of 40, all divided by 13. Right, I just divided both sides by 13, and I got this ratio, this fraction here. And that right side is going to equal some decimal. I can type in 18 times sine of 40 divided by 13. Actually, let's go ahead and do that and just get an approximation to clean this up. So that's 18 times the sine of 40 divided by 13. So that's 0.8900, so 0.89 is good enough. And so then my next line as I'm solving this problem, I'm going to say, okay, so the sine of this unknown angle B equals 0.89. Remember, I'm solving for angle B. And it's on the left, but there's a sine over there. What do I do at this point, everybody? Okay, so if you want to cancel out a trig function, a sine, a cosine, or a tangent, you take the inverse of that function on both sides. So in this case, to solve for an unknown angle, we'd have to use sine inverse. So I'm going to say B equals the sine inverse of 0.89. So that's that little -1. You have to press second or shift on your calculator first. So you have to do the sine inverse to cancel out the sine. And if we do that, so second sine inverse of 0.89. Anyone else get 62.9 approximately? So then B is approximately 62.9 degrees. And now we have another angle. All right, so the law of sines, sometimes you're just solving for a side length, where it's very straightforward. If you're solving for an angle, there's just one final step of taking the sine inverse to get that angle. And that's honestly as hard as this is going to get, taking the sine inverse. So that's right here, 62.9 degrees. All right, so now what's left is side C and angle C. Which one of those is very easy to solve for right now? Why is angle C easy to solve for? Because we have the other two, right? We know A and B, and we know that all three have to add up to 180. So right off the bat, I can solve for this angle C just by subtracting those other two from 180. So that's 77.1. And now we'll use law of sines one more time to solve for side length C. Can all of you do that real quick? So go ahead, set up your ratio and solve for C right now. You already? Awesome. Did you get it too? You did. You got it first, by the way. Yeah, good, good. You got it, you got it. Yes, that's it. So you got it set up. So just do that cross multiplication. So multiply one diagonal and set it equal to the product of the other diagonal. That's right. Yeah, good work. Getting it? Setting it up? Nice. You got it there. Excellent. Still working. Is it this one? You forgot to close the parenthesis after the angle. And so you took the sine of 77 divided by sine of 40 all at once. So make sure you close off the parenthesis after you do each like sine and cosine. Getting it?
Yeah.
So the 77 over C, right? We don't know that one. This, though, can be any other combination with either the A's or the B's, because I know angle A, side A, I know angle B and side B. So you can pick either one of those, the A's or the B's, for that second fraction. So you can do like sine of 40 over 13, or you could do sine of 62.9 over 18. And both of them will give you the correct answer. All right, so my first fraction can be either the B's or the A's. I know both of those values. So I could say, hey, the sine of angle A divided by 13 equals, now this fraction should be the side that I'm looking for. Or if you did this angle first on the left, that's also fine too. We get the same thing when we cross multiply. So C was 77.1 divided by C. And we cross multiply. And C equals approximately, was it 19.7? I think most of you got. Yeah? What'd you get? Did you? 13 times sine of 40. So you have to multiply the diagonals. You did 13 times sine of 40, top and bottom. You need to multiply across. Just like here, I would do this product. All right, there's one thing that I want to show you that I'm not going to assess you on, but you do need to be aware of it. It may show up in a future math class. The way that these problems work is, notice that I've got an angle, a side length, and another side length. And the tricky thing with that is, if I've got the diagram, we're in business, we're good to go. But some problems, you're just going to be given the values just like in a sentence. Like you'll say angle A is 40, side B is 18, and side A is 13. Just written out, and you have to draw your diagram from that verbal description and then try to figure things out. If you don't have the diagram, though, and you're given an angle, a side, and then another side, Well, we run into this issue. So if this is a 33 degree angle, and I know that this side has to be exactly 10 inches, this side, I don't know how long this side is. This side can be any length because it's not given to me. I can calculate it. I also don't know what this angle here is. This can be any angle. I can swing that one side any way that I want. But then this last side has to be 6 inches. And it's got to touch this dashed line, this side B, but I don't know how long B is. But if I think about it, think of this green side swinging back and forth. There's actually 2 different triangles that it could create. Because if this side has to be 6 inches, it could go there or it could go there. And it would still have an angle of 33 degrees, this side of 10 inches, and that next side of 6 inches. And because this angle, it could be that shorter angle or it could be this bigger angle. It could be this shorter side length or it could be this longer side length. It creates 2 different triangles. This is what's called ambiguous. The word ambiguous means there's no definitive answer. And that's because there are 2 different possible versions of a triangle that could be created. I don't know what the angle is. I don't know what that last side is. And so if you're ever given an angle followed by the 2 side lengths across from it in a row, it doesn't always work. Now, if you remember all those side angle side theorems from proofs in geometry last year, remember how fun those were? There was one combination that never ever worked. And that was the side angle, or SSA. You probably thought it was funny if you flipped those letters around, though, didn't you? And we have a little snicker. It's a potty word. All right. And so that postulate doesn't work as a proof in geometry for this exact reason. Because if I'm given an angle followed by a side and another side, there are 2 different triangles that could be created. So I can't assume that given those 3 properties of 2 different triangles that they are congruent, because it could be, this first triangle on the left, and then it could be this second triangle on the right. 2 different triangles with those same 3 criteria, but they're 2 totally different triangles. So that's why the ASS postulate wasn't a thing last year in geometry. It didn't actually work. And this is just a reason why. Same thing when you're using the law of sines. If you're just given these values without the diagram, sometimes it won't work or you won't get a solution. Like this side, if it weren't 6 inches, if it were like a shorter side, what if it were only like 1 inch? Then it would never make it all the way down to the other side. So sometimes you're given values that don't actually create a triangle and there would be no solution. I'm not going to be giving that to you this year in Algebra 2, but I want you to be aware of it, okay? It can come up in future math classes. Everyone okay with that? Cool. Hey, look at this. It's a word problem-ish. Not really. All right, so now I'm just giving you these values with their labels, A, B, and C, or just A and B in this case. And we had to solve the triangle. We need to find angle B, angle C, and side C. But there is no diagram here, so we're going to have to create the diagram ourselves. So everyone, go ahead and draw the triangle. Now remember that your drawings in geometry don't have to be accurate as long as they're labeled appropriately. So you can even just draw just the most basic triangle ever. You don't have to make sure that the angles are exactly 35 degrees or that the side lengths are exactly 14 and 6. You're just going to draw some triangle. And I'd probably start off by labeling my A, B, and C. And you might have a different drawing than me, and you might have it labeled differently than me, and that's fine. So I might just do A, B, and C. And so this one angle I'm given is the 35 degrees. Side A is 6. And that's given to me. I need to make sure that that 6 is across from the 35 degree angle because those are both A's, and that shows you that they match up. I don't know angle B, but I know side length B is 14. And then this last side that's not labeled, that would be lowercase c. I don't know what that one is yet. So can we use the law of sines for this problem, everyone? Do we have the right combination to get started? Yes. We've got a side length and an angle across. And that would be the A's. I have angle A and side A. So that's going to be my first fraction. My second fraction could be either the B's or the C's, but since I don't know any information about angle C or side C, I'm going to use B, because I know what side length B is. It's 14, and I'm going to solve for angle B. Solving for an angle, meaning we're going to have to use sine inverse again in our last step after we cross multiply. So 14 times the sine of 35 divided by 6 will equal the sine of angle B. So I cross multiplied and I divided by the 6 all in one step. It's pretty fancy, I know. So we can go ahead and multiply that out. And by the way, those of you with a fancy schmancy graphing calculator, you can just take the sine inverse of this entire calculation on the left side all at once. It makes it a little bit easier, gives you more exact values. So I could just do second sine inverse of this whole fraction. 14 times, oops. Yeah, that's right. 14 times the sine of 35 divided by 6. So this is just that fraction right here. 14 times sine of 35, 14 times the sine of 35, divided by 6, divided by 6. Then I need to take the sine inverse of it to get the B all by itself. So I took the sine inverse of it. Oh, error. Anyone else get an error? Yeah. Wonder what's going on here. Well, let's see, what do we get if I just do this division here? You get 1.3. All right, so we've got the sine of angle B equals 1.33, and I need to take the sine inverse of 1.3. But you can't take the sine inverse of 1.3, can you? You get an error. Any ideas why? It does not form a triangle. This would be that ambiguous case that I told you about on the previous slide. So sine and cosine, like when you're taking the sine or the cosine of an angle, if you think about it in terms of like a right triangle, and you don't need to write this down, this is just for your own knowledge. If I've got this angle here, I don't know, like 40 degrees or whatever, the sine of that angle has to be this leg, the opposite, divided by the hypotenuse. Right? Isn't that sine? So in SOHCAHTOA, the opposite divided by hypotenuse. Now, if that ratio of opposite over hypotenuse, if it's, in this case, 1.33, right? That's what we had. The sine of that angle equaled 1.33. If a fraction equals 1.33, does that mean the numerator is bigger or the denominator is bigger? If you have a value bigger than 1, which is bigger, the O or the H? The O would have to be the bigger value, right? Like 10 divided by 2 gets you a number bigger than 1. If it were 2 divided by 10, you'd get a decimal, a 0 point something. But since this is 1 point something, meaning it's bigger than 1, that tells us that O is the larger value. Now let's go back to our right triangle. Is O allowed to be bigger than H on this right triangle? Why not? Hypotenuse has to be the largest or the longest side. So if you ever have something that's like the sine of some angle or the cosine of some angle, and you get a value of like 2, 1.5, anything bigger than 1, you know that that can never happen, because that would indicate that the hypotenuse is not the longest side on that triangle. So in this case, there'd be no solution. For this example here, what that means is that these values cannot form a triangle. Just doesn't work. Basically, with this 35-degree angle, this 6, like if I drew it to scale, this 6 is too short to ever reach that top side, that C. It's never going to be big enough to reach up there. And so these 3 values that I gave you of angle A, side B, and side A don't actually form a triangle. I know, tricky, right? But also kind of nice, because now you get to stop right here instead of solving for everything else. Sometimes it's nice. All right, so this one does not form a triangle. Oh, I guess we're done. Any questions? What's that? You want to know if there's some extra practice you can do right now for the next half hour? Oh, great idea. I happen to have some practice already printed out for you, because I thought that some of you might really be looking to do some extra math, because you love math, don't you? It's okay, you can lie to me. Thank you. I appreciate those stretches of the truth. Is he being nice? April Fools for your love of math. You did. Oh, you trickster. All right, for those of you at home, you may already have found this, but on my P-Learning calendar, there is a wonderful worksheet with some practice problems for you to engage upon yourself. And also anyone here, if you want to grab out your Chromebook, I do have the answers to all of these posted on my P-Learning calendar. Go to calendar, go to today's law of sines, and you'll see practice right here and practice answers right there. Not the whole like solution, but just if you want to see, did I get that correct final answer? And so go ahead and check that out. And you've got a little less than half an hour to make sure you really have this topic well learned. And on the front side, I'll make this a little bigger for you. You've got some diagrams. Also notice that these problems are just asking for one part of the triangle, not the entire triangle, okay? So my examples today were solved for all the things just because I wanted to get you extra practice. But here it says find QR. That would just be this side length from Q to R, which is, look at that, already across from the one given angle. So that should be pretty easy for you. These ones are solving for just the angles. Hey, what do we need to use to solve for an unknown angle? Inverse, right? So make sure you're using your inverse there. 5, 6, 7, 8. These ones, again, you're just solving for a side length in the first two. You're solving for an angle in the second two. And then on the back, I've got 4 word problems. You're going to have to just draw out the triangle to try to figure out what this picture is trying to show you. And these are kind of the applications. These are real world scenarios where it would be useful to know what different sides are of triangles. If any of you ever watch any type of like police type of shows or detective shows, a lot of times when they're tracking a bad guy, like through their cell phone, you might hear them say, "We triangulated the signal." And you never hear that, like, "Oh, we can triangulate him, this or that." Anyways, it's a technique that they use to like figure out, oh, it pinged off of this cell tower and this cell tower or something. So we can build two sides of the triangle. I can figure out what those two angles are, and then I can pinpoint his location being the third point of that triangle using trigonometry. Basically, you're all now Batman because you know trigonometry, because you can solve all kinds of crimes. You're welcome. Please tell your parents that you're all now Batman and that you are dropping out to become a crime-fighting vigilante.